This is the video on momentum and impulse. So we started off this unit by doing the rocket sled challenge. So in the rocket sled challenge, the goal is to launch the front of 3 carts as far as possible. The challenge will consist of 3 launches over the next few weeks. The team that launches the front cart the furthest uh, on that third launch will be the winner. So you can see here it's 3 carts launched. You can put your competitors on there and you're pushing, and you want that front cart to go the farthest. So without knowing anything about momentum and impulse, the first launch is usually chaotic, because if you don't know anything, you're just going to be pushing off these carts, not really knowing where to place students, how to push. So before we learn about momentum, we need to review a little bit about Newton's first law and talk about inertia. It's the property of all material bodies to resist a change in their motion. Now, mass is the measure of the amount of inertia a body possesses. So if we recall back to Newton's first law, object in motion remains in motion, object at rest remains at rest unless acted upon by an unbalanced force. So that is Newton's first law. Now, that property of a body to keep moving is called momentum. So if we're looking at momentum, it depends not only on how much mass an object has, but also how fast that mass is moving. So momentum is the product of mass and velocity. Momentum is a vector quantity, right? That arrow over that P means that it's a vector quantity, which means it has both magnitude and direction. Now, we use P to represent momentum, and why P? It comes from a Latin word, but also M was already taken. The unit for momentum is kilogram meters per second. You just take the unit for mass, multiply it by the unit for velocity, kilogram meters per second. So let's take a look at a problem. Let's just say you have a 5 kilogram bowling ball moving down a bowling alley at 5 meters per second. How much momentum does it possess? I just take mass times velocity, 25 kilogram meters per second. Now let's just say if we have that same bowling ball, same 5 kilogram bowling ball moving at negative 5 meters per second in the opposite direction, what would the momentum be? Well, it's negative 25 meters per second. So momentum is a vector quantity. It has a direction, and it's very important. So I've got mass, and it depends on what direction it's moving. Now, this comes into play more when we're talking about collision. So you need to keep track of what direction that object is moving in. So let's take a look at some questions here. As an object falls freely, does its momentum increase, decrease, or remain unchanged? The momentum would increase because the velocity is increasing as it falls. At least the magnitude of the velocity is increasing. Explain how it is possible for an object's momentum to decrease if its mass does not change. What must the object be doing? So if we look at the equation for momentum, that object must be slowing down because the velocity would decrease. Which has more momentum, a large truck at rest or a small car rolling down a hill? The small car, because it's moving. The truck does not have momentum because it is at rest. So now let's take a look at this question. Which has a larger momentum, a tennis ball or a bowling ball? So if we look at these, right, which object resists change in more, or it resists change in motion more? It's going to be the bowling ball. If you toss the bowling ball around, you're going to feel that resistance. Now, resistance to change in motion is inertia, so that bowling ball has more inertia. And mass is the measurement of inertia, so that bowling ball has more mass. Now, what would you need in order to know the answer to the question, which object has more momentum? The bowling ball will always have more inertia, but momentum also depends on the object's velocity. If an object is at rest, that object doesn't have momentum. So under what condition could the tennis ball have more momentum than the bowling ball? Well, if the bowling ball's at rest and you just roll the tennis ball a little bit, it's going to have more momentum. So now let's answer this question. Why would you want your phone to fall on something soft and not concrete? Probably thinking the obvious answer, right? The obvious answer, I don't want it to break. Well, why is that? So in order to look at that, we need to talk about change in momentum. How do you gain one momentum? How do you lose momentum that you already have? In other words, what does it take to change one's momentum? So if we look back to Newton's laws, to produce a change of velocity, a net force must be applied. That's Newton's first law. Now, to produce a change in momentum, we invented a new word, impulse, right? So impulse is change in momentum. You apply an impulse to an object, well, that momentum is going to change. Now, the calculation for impulse is the force applied multiplied by the time interval the force is applied. Or to write it mathematically, force times delta t. Now, that delta means change in. Now, impulse also equals change in momentum. So we know impulse equals mass times change in velocity. So if we put it all together, well, the force times the time interval equals the mass times the change in velocity. So these are all the same questions. Change of momentum. Well, if you change your velocity, the momentum changes. Well, change of momentum is impulse. Impulse is force times the time interval. And the last one, I just expanded out the change in velocity. Final velocity minus that initial velocity. So there are 5 key components to impulse. Impulses always occur in pairs. Impulse pairs always are equal in magnitude. Impulse pairs are always oppositely directed. Impulse pairs always occur simultaneous. Impulse pairs never cancel because they act on 2 different bodies. These should look very similar to the same components of Newton's third law. So let's just take a look at this. Let's just take a look at somebody throwing a ball in a boat. Newton's third law tells us that there is a force acting on the ball and a force acting on the person in the boat. So let's take a look at which objects exerts a larger force in magnitude. Well, they're going to be the same. That's what Newton's third law tells us. Now, which of these objects exerts the force first? Well, force pairs are simultaneously. They start at the same time. Which object applied the force for a longer period of time? Force pairs are simultaneous. They're applied for the same amount of time. Now, if the force pairs are equal and opposite, why don't they cancel out? They're acting on 2 different objects. One is acting on the ball, and the other is acting on the person in the boat. So which object experiences a larger impulse? Well, we know that the force applied to each of the objects is the same, and we know the time interval that the object is the same, so that it's going to be the same impulse. So which object experiences a larger change in momentum? Impulse is change in momentum. If they both have the same impulse applied to them, they're both going to have the same change in momentum. Now, why is the effect of the same impulse different on the objects? Impulse is change in momentum. Well, if we look at this, we know that the force applied to that ball and the person in the boat is the same, but what happens is that person in the boat has a much larger mass than the ball. So the ball must have a larger change in velocity. But they both have the same impulse, both same change of momentum, right? But one has much lower mass, so it has a larger change of velocity. That's why it goes faster than the boat going backwards. So in order to look at this concept, we looked at bungee, right? So we tied a bungee cord to like a Coke bottle, and then we tied it to a nylon cord, and we dropped the Coke bottle into those 2 different circumstances. So we're just supposed to observe how it comes to rest. So in both of these scenarios, they have the same mass, right? You're dropping the same we didn't change the object. So in order to answer the rest of this question, why do people bend their knees when landing? So let's just take a look at this, right? So let's just assume it's the same person jumping from the same height. You're jumping off a table, you're landing on the ground. Let's just say you bend your knees in one scenario and you keep your legs straight in the other scenario. Ouch, right? You know that that's going to hurt. So in which of these scenarios does that person experience a larger change of velocity? It's going to be the same change in velocity because both scenarios, whether you bend your knees or you keep your legs straight, you're coming to rest. So which of these does the person experience a larger change in momentum? Well, if it's the same person, it's the same mass coming to rest, same change in velocity, it's going to be the same. Either way, you're bringing the same person to rest. So it's going to be the same change in momentum. Well, this next question is about impulse. Impulse is change in momentum. In both of these, both of them experience the same impulse, have the same impulse applied to them. So this is the key to it. In which of these scenarios does the person take a longer time to come to rest? So it's going to be bending your knees. In which scenario does that person experience a larger force? Well, you know that if you jumped off a table and you kept your knees straight, you know that that's going to hurt. You're going to experience a larger force. So what variable does bending the knees increase? It's going to increase the time interval that that force is applied. What variable does bending the knees decrease? It's going to decrease the force that is experienced. So if we look at this, same mass, same change of velocity, right? Now, the time is what you can manipulate. You want to spread that time out as long as possible, which will lower the force, right? If you kept your knee straight, you're going to stop really quickly, but you're going to experience a larger force. So that has to do with the bungee jumping, right? So when we looked at bungee, right, we had the same bottle, right? One was attached to a bungee cord, one was attached to the rope. So in both of them, same change of velocity, that bottle came to rest, larger change in momentum, same bottle, same end result. They both come to rest. Same change in momentum, same impulse. Impulse is change in momentum. the person takes a longer, or that bottle takes a longer time to come to rest when it's attached to the bungee cord. So the bottle will experience a larger force experience a larger force when that static rope, just a regular nylon cord. What variable does the bungee cord increase? It increases the time that the force implied, which decreases the force. Right, so you can see in these two pictures, one's a bungee jumper, right? One's a person, assuming same person, falling from the same height. Right, now the bungee cord, that stretches the time out that the force is applied, which lowers the force. Now, that picture off to the right is a clip from the Mummy, the movie. So it's not a real person being, it's just a stunt. But that's why, like, when they would hang people, it's supposed to be a humane way, because what it does is it applies a very large force to the neck, which would have broken the neck, because what it does is it brings you to rest really quickly, which increases the force, right? But just want to put a disclaimer out there. It's not a real picture of somebody hanging. It's just a clip from a movie, right? So from the Mummy. It's a good movie. All right. Anyway, so that brings us to those last questions. We already kind of answered this in both, like with that bungee cord, is that in both of those scenarios, the bungee and the nylon, it's same change of momentum, same impulse, same change of velocity, same mass, but the difference is that bungee cord stretches that time out, or stretches the force out over a longer period of time, right? So the variable that it increases is going to be the time interval, and that it decreases the force. Why do cars have airbags? So let's just take a look at airbags. Assuming the same person, right? The same person hitting a car or hitting something, going the same speed, they're gonna experience the same change of velocity. Either way, whether you hit the steering wheel or you hit the airbag, you're going to come to rest. Same change of velocity. Assuming the same person, same change of momentum, because you're bringing the same mass to rest. So it's going to be the same change of momentum. Impulse is change of momentum, right? Impulse had to be applied to this person to slow them down, to take that momentum away, right? Now, when you hit an airbag spreads that force out over a longer period of time. It takes a longer time to come to rest. So the variable that the airbag increases is time. It decreases the force that's experienced, right? Same person coming to rest, it's going to be the same change of momentum, same impulse, but what that airbag does is it increases the time that force is applied, which decreases the force. How can you use your knowledge of impulse to take a punch? So what I want you to see in this one, right, no matter what you do in a punch, right, whether you lean into it, whether you stand there, whether you lean back and go with the punch, either way, that fist is going to come to rest, right? So what you want to do is you want to minimize the force by extending the time that it takes that fist to come to rest. That's why you would want to lean away, right? So if the person leans away from the punch, that will increase the time the force is experienced. If the time the force is experienced increase, this will decrease the amount of time the person experiences. So same result, that fist comes to rest. But what you want to do is you spread the time out over a longer period of interval, and that decreases the force. Does armor protect you from a fall? So the answer is no, right? Because what you should have gotten out of this is that armor doesn't really decrease the time that it takes to come to rest, right? What armor does is it really protects your skin. It spreads impact out over a larger area, like if you're getting hit with a sword, but it doesn't really protect you from a fall. Now, how can you throw a ball as fast as possible? So let's just take a look at a couple scenarios, right? So this one's the exact opposite. This one's throwing something even farther and faster. And what you want to do is, like, just think about this. If you're using a wrist, right, just your wrist, you're only applying the time or force for that quick amount of time. Now, if you use just your elbow, right, you're only applying it for a longer period of time, but not much longer. Now, if you use your whole body, you're applying that force for a much longer period of time. So in this one, we're applying an impulse to an object to speed it up. So you can see here that the idea is that if you use your whole body, you're applying a force over a longer period of time. You might be a little stronger, right? If you're using your wrist, your elbow might be a little stronger, but what that does, by using your whole body, you're applying that force for a longer period of time. So, once again, just as a final thought, there's too much unknown in the universe to take a break from learning. Get out there and question everything.